Hello, welcome to Superphysics, the online physics tuition service. This video is about question 4 from the WJEC AS Physics Unit 1 exam 2016 as part of the new specification. So question 4 is about materials. It's about the classic Young modulus experiment. We have some text here from a textbook describing a method how to determine the Young modulus of a metal. We've got a method here, got a diagram, and a bit more method on the bottom here as well. So let's read the questions first of all, and then we'll see what we're looking for in the actual text. Explain how the effect of a change in temperature on the wire is minimised. Well, let's go to the top, shall we? It says a long test wire, that's quite important, it comes out later on. A long test wire and a reference wire of the same length and material are suspended from a common rigid support. This minimises the effect of temperature and the movement of the support. Okay, so because these two wires here, the test wire and the weighted reference wire, because they're made from the same material, any change in temperature is going to affect them in the same way. Okay, so we can say the test wire and reference wire are made from the same material. Okay, and because we need to explain that, so that's one mark. It says wire are made from the same material, so any change in temperature affects them both in the same way. Okay, and that's your explanation. That will give you 2 marks. Okay, question part 2. State what is meant by the term elastic limit and explain how an experimenter would know whether or not the test wire has extended beyond its elastic limit. Well, the definition for elastic limit is up to that point the wire would return to the original shape and length. Beyond the elastic limit, you get something called plastic deformation, which means that once you take away the load, or the weights, whatever it is, the wiring remains permanently stretched. So elastic limit is the point at which the wire does not go back to original length and shape. Okay, 1 mark. We need to explain how an experimenter would know whether or not the test wire has extended it. So, if the load is removed and the wire does not go back to original length, it has exceeded its elastic limit. And that's how the experiment will know. The textbook also states the apparatus and procedures are designed to carefully minimise uncertainties when taking measurements. States why the long wire, that's the long wire we said here at the very start, a long wire, is used rather than a shorter one. Well, it's a bit like if I'm counting pound coins and you have £1,000,000 coins and I miscount by £10 coins, it's going to make not much difference to the overall amount of money I've counted you to have. However, if you've only got, say, £15 coins and I miscount by 10, that's going to make a huge difference to the amount of money I've counted you to have. And the same thing here, the smallest, if your wire is very short, any mismeasurement is going to make a big difference to the overall measurement of length. So a longer wire is used to minimise that uncertainty when measuring length. So it's to improve accuracy by reducing the uncertainty. and that's how using a long wire is used for that very reason. Part 2, why is the diameter measured at several different places? Well, that's to improve the accuracy of measuring the diameter and therefore calculating the cross-sectional area. So it's to improve accuracy in the cross-sectional area by calculating a mean diameter. So typically you measure the diameter using a micrometer at 3 or 5 different places, and then calculate the mean diameter and use that to work out the cross-sectional area. Okay, let's move on to part B, where we start looking at some calculations. Here we have a typical graph showing the results of such an experiment given below. The original length of wire is 2.4 meters, and the mean value of diameter is 0.32 millimeters. Okay, and we've got the loads here, which is the force, and we've got the extension on the bottom here. Use the graph and the measurements to determine the Young modulus of the material of the wire. So the Young modulus is given by the equation, capital E, which stands for Young modulus, is the stress over strain, or in shorthand, sigma over epsilon. That's different from the sigma in the Vine displacement law. That's very different. Again, physicists, we use symbols from different contexts. So sigma is the symbol for stress, and the epsilon there, it's not EMF, it's actually means strain in this context, but again, it shouldn't cause too much confusion. So the formula for stress is force over area. The equation for strain is the extension over the original length. Okay, so what we can do is we're going to put all these equations into one equation. So sigma is force over area, and we're dividing that by the strain, which we know to be extension over original length. Now, to make it a bit neater, we can put it into one. So when we divide fractions, we turn the second fraction upside down and multiply through. So that's the same thing as saying F times L over A times X, or in shorthand, FL over AX. And that's going to give you the equation for Young modulus. Now, we need to use the graph. It says here use the graph. So in some way the graph is going to be useful to us and the measurements taken. So if we look at a graph, if we look at the gradient of our line, now it's always sort of hedging our bets a little bit here. What does the gradient mean in this context? Well, the gradient in this context is the force over extension, essentially F over X. Okay, so the gradient for this graph is F over extension. So if we work out the gradient, then we can multiply by length divided by area to get the Young modulus. So the gradient in this case is we go across to the y-axis. That's going to be 28, and this value here is 4.8. Yeah. So the gradient is 28 newtons divided by the extension, which is 4.8. This is in millimeters. I'm going to convert this to meters just so we're consistent through. We can never ever mix and match units. We have to be consistent with units throughout all our equations. So 4.8 times 10 to the power minus 3. And that's going to be the value of f over x. And let's leave that for there as we are for a second. Well, we could work it out actually, so let's work it out. So we're going to do 28 divided by 4.8 times 10 to the power minus 3 gives us 5,833.3 recurring. Again, I'm going to store that in my letter A. Okay. So now we're left with Young modulus, capital E, is f of x, or the gradient, so 5,833.3 times by L, which we know to be 2.4, divided by the area. Now we're told the diameter is 0.32 millimeters. We always assume wires are cylinders, so the cross-section area is going to be the area of a circle. So it's pi. Don't be confused here. This is the diameter, so the radius is 0.16. And because it's in millimetres, that's in metres, we're going to keep everything in metres to make it easier for ourselves. So 0.16 times 10 to the power of minus 3, all squared, pi r squared on the bottom. So that's formula calculation, so alpha A times by 2.4 divided by pi r squared, so shift pi times 0.16 times 10 to the power of minus 3, all squared, gives you an answer of 1.74 times 10 to the power of 11. Now my units here. The units for stress is a Newton per metre squared. The strain has no units because it's metres divided by metres, so the units for your modulus is going to be newtons per metre squared. Okay? Last part of the question. Calculate the energy stored in the wire when it's extended by 2.4 millimetres. So the equation for energy stored, E equals half Fx, so half times force times the extension. So the half times by force. So when it's extended by 2.4 millimetres, we need to go to the graph and find 2.4. Now 2.4 is there, that's 2.4. We go up to my line, which is here, go across, and that's going to be 14 newtons. So half times 14 times by 2.4 times 10 to the power minus 3, and do 0.5 times 14 times by 2.4 times 10 to the power minus 3 gives you an answer of 0.0168 joules, and that will give you your energy stored in the wire. Okay, if you've got any questions or comments, please leave them in the section below, and now we're going to move on to question 5.